ಮಾಡ್ಯಾ ಎರಡು
ಏನಾದರೂ ಇದು ಸ್ಕ್ರೀನ್ ರೆಕಾರ್ಡ್ ಡೌನ್ಲೋಡ್ ಮಾಡ್ಕೊಂಡು
ತೋರಿಸ್ಕೊಡ್ತೀನಿ ಟೈಮ್ ಎಷ್ಟು ನೋಡ್ಕೊಂಡು ಸ್ಟಾರ್ಟ್ ಮಾಡಿ. Hello, good afternoon, students. In this today classes, so let me start the first part of fifth module. ಇದು ಹೋಸ್ಟ್ ಮಾಡೋದಕ್ಕೆ ಸರ್ ಕ್ವಶನ್ ಹೋಸ್ಟ್ ಮಾಡಿ ಸರ್ ಯಾರನ್ನ ಈ ಕ್ವಶನ್ ಏನು
ಜಸ್ಟ್ ಪ್ರೆಸ್ ಮಾಡ್ಕೊ ಮೇಕ್ ಹೋಸ್ಟ್
ಅವನು ಏನು ಮಾಡ್ತಾರೆ ರೆಕಾರ್ಡ್ ಮಾಡೋದು ಹೇಳಿದ್ದೆ ಸರ್. Hello, dear students. So we are starting the first part of fifth module, that is instrumental analysis of instrumental methods of analysis and nanomaterials. Already the nanomaterials is over, so only we are waiting towards of these instrumental methods of analysis. In this, the first instrument we have used to estimate the how much of the salt is there, how much of solute is there. So this is also nothing but the quantitative. So we have used the instrument for qualitative assessment is the atomic absorptions and polarography, including of fluorescence method and polarographic methods, those are there. But in our syllabus, in the colorimetry and flame photometry and including of what we can call it as a potentiometer, conductometer, flame photometer. So totally these 5 to 6 instruments we have used to estimate, not qualitatively. These are also we can use it for quantitatively. In this quantitatively, suppose you have prepared the solution at the time, how much of the salt is weighed, supposed to forget, or even after you can weigh the salt also, you cannot note down, you properly not note down. So don't throw the solution, don't throw the solution, because it can be, you can noted as you can changing into as the labeled cells. This is also we can changing into as a known solution, standard solution. For this we can get the what we can call it as prepare the one more standard solution. So afterwards these the unknown solution we can label. For this we can using the one of the instruments what we can call it as colorimeter. The name itself indication of this using of the solution based on colors and based on thickness, based on concentrations. So these say we can note down that concentration, no problem. If not note down also no problem, by using of this colorimetric method, so we have to follow. So in this colorimetry, the principle, the already we have explained the how to using of this colorimeter in this estimation of fluoride in the water sample. For that, what we have done, so we can taking the 50 ml volumetric flask of 6 to 7. To that, first we can prepare the standard the sodium fluoride solution. How you can going to prepare? So weighing of 1 gram or the 1 gram of sodium fluoride solution, sodium fluoride dissolved in 1 liter. From that, we can prepare out the 10 ml. It contains 10 milligrams of sodium fluoride. Again, it is dissolved in 1 liter of DM water. So that is, we can call it as a stock solution or standard solution, which is used to estimate the fluoride through colorimetrically. So you keep aside. Then you can prepare that the Spadans reagents also. So that is enough. Afterwards, you can take this 10% of sodium arsenate oxides or sodium bisulfates also you can use it. Sodium arsenates you can use it. So first you can label it as, you can take it as first one. Second you will take it as labeled 1, 2, 3, 4, 5. To first you can add sodium fluoride is 2 ml. Second one you can add 4 ml. Third one you can add 6 ml. Fourth one 8 ml. 10th one 10 ml. Fifth one 10 ml. For this, next you will add to all 10 ml of Spadan reagents. It is common to all. You can add it. So that's both. Then you can add so 1 drop of sodium arsenate oxides towards. So you can add remaining ml. The first one 10 ml plus 2 ml, remaining 38 ml of 38 ml of DM water. So second one 36 ml of DM water. Third one 34, fifth one, the fourth one 32, fifth one 30 ml. So afterwards, you can take one more 50 ml volumetric flask. To fill that, suppose you will take the 10 ml of water sample. To that, you can add 10 ml of Spadan reagents and 1 drop sodium arsenates also. Sodium arsenate oxides you can add it. Afterwards, you can prepare one more, that is, we can last one, sixth one, we can call it as a test solution. The first one, before that, you can prepare one more 50 ml, you will take it, one blank solution. To that, don't add the sodium fluoride. To that, you can add only the 10 ml of Spadan reagents and remaining 1 drop of that sodium arsenate oxide, followed by you can add 40 ml of DM water. This is used to at 570 nanometer the fix this and to read the absorbance at 570 nanometers. You can using off, you can using off calibrate the instrument. You calibrate the instrument. Afterwards, you can taking this, make it 0 0. You draw the two columns. In the first columns, you can rate it as 2 ml, 4 ml, 6 ml, 8 ml, 10 ml. So everything is going on. So the last one is last one is you can label as test solution. So then it is this taking as 0 0 recorded. First one you have taken 0.06, you will get it. Second ml you will take it as 0.12, you will get it. Third one you will take it as 0.18, you will get. Fourth one you will get as 0.24. Fifth one you can get it as 0.30. So as the same way, so you can get it all those things. The sixth one, that is test solution, also you will get it as, this is what you can call it as 30.308 will come automatically, that it contains 10 milligrams in 1 liter. As the same way, it is also containing of divided by 10, so that is 0.30. So into sodium fluoride is sodium is 23 plus fluoride is 19, 32 divided by total molecular weight. This is the calculation part. As the same way, we are using in the lab is copper sulphate. We find out, estimate this how much of copper sulphates is completely dissolved in 1 liter of DM water. So you have prepared. So in that, so the instrument we have used this meter is, we can call it as a colorimeter. So based on this principle is we can follow on the two principles. What is these? One the two laws we can combusted. We can call it a combined the two laws. Those are Beers-Lambert's law. So in this Beers-Lambert's law, According to this law only, the instrument will work. The instrument absorption of the light radiation followed by the emission also. Absorption and emission is only the under the instruction of this Beers-Lambert's law. So far, it satisfies the Beers-Lambert's law. So in this experiment, the principle is colored solutions of the properties absorbing the light radiation at specific wavelength, and this absorption and emission is satisfied holds good or accordance with the Beers-Lambert's law. So then it is we can call it as a colorimetry experiment. If not satisfy the Beers-Lambert's law, you won't call it as this is a colorimetry, because the colorimetry is only satisfy the Beers-Lambert's law. So before you can go into that, so what is there in this colorimetry? One light source is there, followed by one filter is there, followed by water sample. You can taking into that, we can call it as a cuvette. So followed by, so one photo cell is there. This photo cell is absorbing that radiations. Then we can record it either by machine itself is also, we can using the sophisticated equipment. In that we can do it. The first one is light source. Then it is it can diagnose or estimate under only the visible spectrum, not beyond that. That is 400 to 900 nanometers. We can use it to estimate of the how much of the salt is completely dissolved in 1 liter of DM water. So that sample is you can taking into this one with small test tube, we can call it as a cuvette. So afterwards, passing the light. Source is there. Filter according to this only we can get the light rays off under the visible spectrum. That is 400 to 700 nanometers. Afterwards, passing that light through this cuvette. So it is free from all these divide, it is any scratches, it should be free from all impurities. So it afterwards you can go to this, the light rays is pass on to the photo cell, that is absorb that radiation. Afterwards that absorbance is we can showing in the number, that is showing on the recorder. You can note down also. This is the usual, you can taking any samples you in the cuvette, you keep it in that cuvette into the where the space providing on the colorimeter, and you can note down its absorbance. We can plot the graph against of absorbance and volume of a copper sulfate. Volume versus absorbance, we can plot the graph. At that of plot the graph, we can get one straight line that we call it as a calibration curve. In that calibration curve, you can get it based on the satisfaction or according to the Beers-Lambert's law only. If not get the this calibration curve, somewhere you can make mistake. You will first going to find out that mistake. Afterwards, you will going to how much of salt is completely dissolved in 1 liter of DM water. You can going to estimate. So far, before going to this assessment, so we can go into this first, we can discuss the two laws. Those are, one is Beers law, another one is Lambert's law. So in this Beers law, so it is first we can it is expressed in this explained. So I is equal to this, I means intensity of light radiations. It is I is equal to IA, it is absorbance, plus I or it is radiations, and the last one is T means transmittance. So in this usually we have taken any of the equipment in that glasswares, 100% of transparent is there. So far no absorbance, no radiations is there, no reflection is there. So far we can, next line is we can write it as I is equal to IA plus IT. A means absorbance is there, T means thickness is there. So in this, So what is this? First we can going to satisfy the law is Lambert's law. So in this Lambert's law, according to this law, the intensity of monochromatic light or emitted light is decreases exponentially as the as the thickness of the absorbing medium increases arithmetically or mathematically. So this is one statement. What is this? You take a one cuvette, so take a one light source, you can taking in the water sample, you can passing on the rays through this test tube. In the initial I naught, suppose 100 rays are there. So in the transmitted also, if 100 rays are coming out, that we can call it as no absorbance, no reflections, only transmission is I naught is equal to IT also. It is completely transmitted, because it is completely transmitted, because completely it is a transparent, so it has happened. Instead of that, you can take that in that taking of what we can call it as 1 gram of any of the salt, you can dissolve in 1 liter. You can taking that solution in liquid, the passing of light rays as usual, keep it into this colorimeter at the time. So it is instead of 100 rays are coming out, transmitted rays, either 99% it will coming out. So it means 1% of absorbance is there, 1% of absorption is there. As the same way, you can increasing the salt dissolving from 1 gram to the 2 gram, so it is 2% is absorbance. Increase to the 3 gram, 3% is absorbance. So like this, whatever you go into this increases of salt dissolving that your standard solution, taking into that cuvette, the thickness of the solution you can increases, the absorption is also increases, the intensity is according to that intensity, it is directly proportional. So far IT is equal to directly proportional of I naught. So in this, thickness is increases, absorbance A is also increases. So thickness is reduces, the absorbance is also reduces. So based on this, uh, we can finally we can explain into as these emitted rays. The emitted rays, according to this absorption of these things, we can call it as a Lambert's law. The Lambert's law, intensity of transmitted light decreases exponentially as the increases of thickness of the solution arithmetically. Increases of these salts, absorption is also increases. So that we can go into this right, explained in that already, we can send to you also. That is minus we have taken this because of this radi emitted from the source is we after absorption is less. So for minus di by dt directly proportional to intensity of the light, that is I naught. So that is you can continue. So after this differentiation, so minus di by dt is equal to k into I, because this is the constant k is this constant. So forward by, so it is you can applying this integration to this before that integration, so minus di by I is equal to k into dt, followed by you can apply these integrations. So then it is 1 by I dot di is equal to k dot integration of dt. So finally you can get it as minus log is equal to kt plus c is the integration constant. When these integrations at the time, so I is equal to I naught, it means initial how much is there, the I naught is also there, the no absorption is there. At the time we can find out the value of integration constant c, then you can substitute all those values. Finally you can get it as a log my log I naught by I is equal to kt. So then I naught by I is equal to e to the power of kt. Finally I naught by I naught, that is what we can call it as transmittance. So the transmittance is equal to e to the power of minus kt. So this is what we can call it as Lambert's law. If satisfy the Lambert's law, 50% of the colorimeter as a satisfied. According to this law only, the thickness as a absorbed. So second law is what we can call it as Beer's law. So this is also same. The intensity of transmitted light decreases exponentially as the concentration of absorbing substances increases arithmetically. That is, it is what is first we can take it as no dissolved salts. At the time 100% radiation, 100% emittance, emittance or transmittance. If 1 gram is dissolved, 1% is reduced. 2 gram is reduced, 2% is reduced. 3 gram is reduced, added, 3% is reduced. 10 gram is, so okay, that 10% is reduced. So it is also given the idea to us, any much of increasing the concentration, that much of decreasing of a transmittance. So far, so this law is what is the intensity of transmitted light decreases exponentially as the concentration increases arithmetically or mathematically of absorbing substances. So this is what we can call it as. Same it is also satisfied by minus di by dc. So C means concentrations and directly proportional to the intensity of the light. So then it is, you can continue that minus di by dc is equal to ki. So followed by, so minus di by I k into dc. So here we can taking this integration constant is a. So you can substitute the value for integration constant a minus log of I. So followed by log of I naught by I is equal to kc. So then I is equal to I naught of minus I naught into e to the power of minus kc. In that first of Lambert's law, so I is equal to I naught into e to the power of minus kt. Here it is equal to I naught into e to the power of minus kc. So both are almost all, you can get it as minus kt here, minus kc here. So multiplied by one another. So multiplied by one another at the time I naught by it we can call it as transmittance. So log of it by I naught by it is we can call it as absorbance. So it is one mistake is there. I naught by it is there for transmittance. You can make it correct. It by I naught is we can call it as transmittance. Log of I naught by it is we can call it as absorbance. The absorbance is reverse of the transmittance. The transmittant is a reverse of the absorptions. So at the finally we can get it as A. Absorption is equal to or directly proportional to this concentration and thickness. So A marpu, it is directly proportional to concentration and thickness. This the sign is we can remove by epsilon. The coefficient of absorbance and thickness A is equal to E of Ct. That is equal to, the absorbance is equal to log of I naught by T. So this I naught is 100%, it means 1. So this log of 1 by T is equal to minus log of T. So this is what we can explain in this theory of colorimeter. This is very essential for us also. So at the time of explanation of colorimetry explained in the for 8 marks, you can write down, and derivations you can write this, what is the principle, followed by what is Beer's law, followed by what is Lambert's law. At least you can 4-5 lines you can derivations we require. Directly you can writing up 2 to 3 lines also. So then it is satisfied. So now we can label the instrument is a colorimetry. Color COLYUR also, COLOR also, no problem. This is from calorimeter. So calorimeter we have used in the module 3 of the estimation of potential, the estimation of energy, heat energy or any of the form of energy. Here it is we can use to how much of, that is quantitative estimations of salt is dissolved. You don't throw it up unknown solution, you can keep aside this. You set up the colorimeter, so afterwards you can set up the colorimeter, so you can check it all those things, source is correct, filter is correct. So afterwards you can take the cuvette, wash with water, so then keep it into the where the space providing you, so you can switch on that photo cell, followed by you can switch on the recorder also. This everything is you can set up. This application is already you have used, this instrument is already you have used in the estimation of fluoride in water sample. Here again we have used for estimation of copper in the copper sulphate. So already you can know it. So what is that? Copper sulphate crystals formulate CuSO4 dot 5 to H2O. So pentahydrated copper sulphate we can call it as a blue colored crystals of copper sulphate. So this is we can also call it due to this color is blue vitriol. So iron is we can call it as green vitriol, and zinc is we can call it as a white vitriol. So all those these sulfates. So if you want to dissolve in this water, 1 liter of DM water, of course we can you not measuring the water also, you prepare the unknown solution, afterwards the same. If you want to find out the percentages of copper, you prepare the copper sulphate solution. Whether it is unknown also, don't throw it. If you want to find out the percentages of iron, you prepare the iron sulphate, that is FeS for a 7H2O, you can take it, weigh that. If not weighed also, you prepare the solution, but don't throw it. So afterwards you prepare the iron sulphate, that is FeSO4 H2O 7H2O sulphate standard solution you have to prepare. So then you will go into estimate. As the same for zinc sulphate also, you prepare the solution, unknown solution, don't throw it. Again you will prepare the standard solution of zinc sulphate, then you will go into estimate. For this colorimeter, it requires 750 ml volumetric flask. How did already you have used in the uh, in that quality quantitative estimations of volumetric or quantitative estimation of gravimetric of first 6 experiments. As the same way, the reducing size of this volumetric flask is 50 ml. So far we labeled as 50 ml volumetric flask. We labeled 1 2 3 4 5 studies enough. So sixth one is test solution. The first one is a blank solution. So for this you can already prepared unknown solution is don't throw anywhere. So then keep aside. So instead of that you can throw it. So you can again you will weigh the 8 gram of copper sulphate with the electronics balance very accurately, followed by, so then you can weighed accurately. It is dissolved in the 1 liter of DM water. So what you have done, you can taking as a 5 labeled 50 ml volumetric flasks, labeled it, then you will take one blank solutions, that is sixth one, another one is test solution. So all these things keep it aside. You prepare the stock solution, that is also we can call it a standard solution. So nothing, the stock solution is nothing but standard solution. From that, whichever you have labeled for first volumetric flask 1, you can fill 2 ml of copper sulphate. For second one, you can add 4 ml of copper sulphate. For third one, you can add 6 ml of copper sulphate. For fourth one, you can add 8 ml of copper sulphate. For fifth one, you can add 10 ml of copper sulphate. Afterwards, you can add all to these 5, 1 to 5, you can add 5 ml of aqueous ammonia or ammonium hydroxides also. When you are going to add it, immediately the light blue color of copper sulphate is turned into this cuprammonium complex, that is deep blue color, you can get it. That is what we can write as Cu plus plus 4NH3 CuNH3 4 times. So the whole is denoted by plus 2. So this is due to this complex ion as formed in that copper sulfate become complex ion, so you can get it of this blue color. This is also we can call it as a skews reagent. Why do you call it as get it as this deep blue color? Because of this copper sulfate forming it as cuprammonium complex, so far you can get it as this blue color. So you can add to all these 1, 2, 3, 4, 5. Commonly you are adding 5 ml of aqueous ammonia. That is also keep aside. Then you will take test solution. How much you want? Whether you want 5 ml you will take or 10 ml you will take. You will take 5 ml of copper sulfate from unknown solution. Then to that you can add 5 ml of 5 ml of ammonia, you can add it. Ammonium hydroxide solution also, or ammonia you can add it. As the same way, the test solution also gets the deep blue color because cuprammonium complex as formed. That is also keep aside. Then you will take one more, that is blank solution. Blank means not empty. So without the test solution, without the standard solution, here test solution is also copper sulfate, standard solution is also copper sulfate. Without the to be tested solution, other reagents you are keep on adding, and it is used to set the instrument, it is used to caliber the instrument. That is we can call it as a blank solution. For that what you can do, so you can take 5 ml of ammonia to the blank solution, then remaining 45 ml of purest distilled water you can add it. So keep aside everything's nearby the colorimeter. Then you will take the that blank solution. So then you can keep it into the cuvette. So you can caliber the instrument, set the apparatus. The absorption at 620 nanometer is maximum. You set the apparatus before calibration of this 00 absorption at 620 nanometer. For this is fixed for copper sulfate. For iron sulfate is also different. For zinc sulfate is also different. As the same way what you already estimated of fluoride, that is 570 nanometer. So far, so you can what you can get it as already keep it. Take the blank solution, set the operator absorbances, make it 0. By make it 0, then followed by you can throw that blank solution. You can fill the 2 ml, first 50 ml of concentrated, that is 2 ml copper sulfate reagents. You can fill to this, fill to the cuvette, take the absorbance, read the absorbance. When the light is passing through from the source to the filter through these samples, finally the photo cell is absorbed. How much of the radiation emitted rays are coming out? Based on that, it is showing up its absorbance is 0.06. If you taking as 2 ml of 8 gram dissolved copper sulfate, you observed light is over, then absorbance reading is 0.06. So afterwards you can throw it. Then you will take the one more 50 ml of volumetric plus, you will take it. So that is you can fill to this cuvette. You can reading of this, keep it into the where the space providing you for this cuvette, followed by you can absorbing the readings. Absorbances you have taken, that is 0.12. Taken the third one, that is 6 ml 50 ml volumetric plus, what it contains, 6 ml of copper sulfate, 5 ml of ammonia, 6 plus 5, remaining 39 ml of DM water. You can just fill to the cuvette, take the absorbance. That is what is the absorbance is 0.18, you will get it. That is the reading. So fourth one you will take it, 8 ml of copper sulfate, then 5 ml of ammonia, so 13 ml, remaining 37 ml of distilled water you have already filled. So pour into this cuvette, take the reading is 0.24. Finally, we will take 5 that is 10 ml of copper sulphate, 5 ml of ammonia, 35 ml of 35 ml of DM water. That reading is 0.30. You will get it. So this is the you can satisfy this both Beers and Lambert's law. You can afterwards test solution is there, that is also pour into the cuvette, take the readings, what it suppose you will get it as 0.15. So it is we have taken already 5 ml. So in all these remaining series of standard solution, 2 ml, 4 ml, 6 ml, 8 ml, 10 ml. But instead of that, we have taken here either 5 ml or 10 ml. So in that, suppose you have taken the 10 ml, so that reading is 10 ml plus 5 ml of ammonia, get the same color of cuprammonium complex, what is already formed in the number 5 of copper sulphate volumetric flask, as it is colored as formed. So that very clearly indicate this is also 10 ml 0.30, that is also 10 ml 0.30. Immediately you drawn the conclusion already what you can weigh this, that is not weigh the salts of copper sulphate or not recorded the copper sulphate of unknown solution is also 8 gram is dissolved in 1 liter. This is the confirmation. If it is suppose 4 gram is dissolved at the time, instead of this for you will take 10 ml at the time, instead of 0.30 absorbance you will get it as a 0.15 absorbance. That very clearly indicates 4 ml of copper sulphate is dissolved. So 1 ml is 0.75, you will get it. So as the same way, we can go into this estimation of percentages also, it is followed by. So far, so any of this salt is dissolved. So at the time, you should not recorded how much of the salt is dissolved. So we can, if you want to label it as known solution, so if it is forget to write it, forget to add it, or forget to not recorded also, don't throw the solution. Again, you will prepare the one more standard solution. So you already unknown solution you mark it. So known solution you can mark it. Then you can fill to this. Take 4 to 5 of copper sulphates, 2 ml, 4 ml, 6 ml, 8 ml, 10 ml, fill to this 5 ml and 50 ml of volumetric flask. Then you can add common to all of 5 ml of ammonia, ammonium hydroxides. Then you can remaining ml. So this 2 ml plus 5 ml plus 43 ml of DM water, you can fill it. Make it all these series of standard cell, make it 50 ml. So put it into the cuvette at 620 nanometer. Why this is 620 nanometer? The maximum absorption taken place. That maximum absorption taken place at the time. So these satisfy the Beers-Lambert's law or Lambert's Beers law. Both are written. So for A is equal to x epsilon of Cnt directly proportional to the concentration and thickness of the solution. You can plot the graph. In this x-axis is the concentration of this copper sulphate, y-axis is absorbance. When it is, you can plot it one straight line, you will get it as that curve, we can get it as a call it as calibration curve. This is the curve starting or arising from the initial, and it satisfies the Beers-Lambert's law. Then that curve we can call it as a calibration curve. If that curve not satisfy the Beers-Lambert's law, you won't call it as a calibration curve. So far, you can get a one straight line, you can draw straight line also, no problem. Afterwards, what you can having the unknown solution, what is the absorbance, you can got it, you can mark it on the y-axis, then come across this calibration curve, the just corresponding to that x-axis, you can draw this line also, how much of ml you have taken, that should be satisfied. Then you can, according to this gravimetric method, we have to calculate it. So what is in that calculated? So from that graph, 8 gram has dissolved, that is 0.008. So So 5 or 10 gram you can take it as, you can multiply it, you can call it as, that is A, that is copper sulphate. Cu is 58 and it is 63.5, it is a molecular weight. So by this 269.5, that is copper sulphate, CuSO4 5H2O. So pentahydrated copper sulphate taking as a denominator, and then it is copper, what is this 63.5 is its molecular weight, you can taking into as. So into what you can get, whether it is 8 into 8 gram as dissolved in that 8 into this 5 ml or 10 ml, what is that, into that you can multiply it. Finally you can get how much of gram of copper sulphate is dissolved in 1 liter, you will get it, that is in the unit of gram. We want to changing into this milligram, it is multiplied by 1000, so you can get it. So at the time, so the unit is changing from gram to the milligram, so you can get it completely how much of copper is there. This you can changing into the percentage, again it is multiplied by 100. So out of this, what is the copper sulphate total multiplied is there, so it is the into the 63 into this 100, you can finally get into as how much of copper sulphate is dissolved. Finally, how much of copper percentages is there in the given sample, is there in the unknown sample. This is the experiment explaining theory, principles, Beer's law and Lambert's law. Is completely, it can asking for this 8 marks. So you can very neatly you can get ready for this. First you can, what is colorimeter you will write, and you can write the Beer's law and Lambert's law. So very I is equal to I naught of e to the power of minus kt, that is for T means thickness, it is Lambert's law. So it is I is equal to IT, or I is equal to I naught of, it is of minus Kc, it is C is concentration, that is Beer's law. So afterwards this multiplication you can get it as, so then you will this prepare this is working on based on this according with the Beer's Lambert's. So far we can call it as Beer's Lambert's instrument also. So due to this, absorption takes place due to the colors and thickness, we can call it as a colorimetry. So without these colors also, based on the thickness, it can go into estimate the how much of salt is dissolved in a given sample. For that, so you don't want analysis of this complete salt. Instead of that, how much of salt, only the quantitative, very accurate quantitative estimations we are using this instrument, we can call it as a colorimeter. I think you may one line define colorimetry. Any type of this, any explanation I can expect is it is chemical analysis through the measurement of light radiations absorption in the region of visible spectrum with known concentration of the substances. What is this? This chemical analysis. What type of the analysis is? What is there in that DM water? We are not going to it. How much of the by the absorption, light absorption taken place. So it is definitely we know it. How much of copper sulphate is dissolved, we don't know. So far we can fix the colorimeter wavelength is 620 nanometer, because maximum absorption takes place at that 620. Then it is, you can prepare the series of standard solution, standard talk solution, in series of standard solution, prepare the blank solution, take the unknown solution, fill to the cuvette, then you can taking these readings. So you plot the graph absorbance against or versus with the um, concentration of copper sulfates. So then you can afterwards plot, you can how much of this copper sulfate is dissolved in 1 liter with the help of the graph, and we can get it. Then you can calculate the how much of copper sulfate is dissolved. So for chemical analysis through the measurements of absorbance of light radiations in the visible region of spectrum, that is 400 to 700 nanometer, with respect to the known concentration, we can call it as a we can call it as what is, we can the colorimetry experiment. So this is for colorimeter experiments. So what we can explain, I think you got it. So any of these doubts you can ask me. So then it is easy for understanding also. So now it is one more we will start it, but time is very less. So we can start this of next experiment. So okay, let me see in the next class. Thank you.